This is week 9 of the problem solving session for applied thermodynamics course. So, previous week we saw about psychometrics and how to do problems on psychometric air conditioning and so on. And this week we go into combustion and we'll calculate how the complete combustion is and how much air is being used, the stoichiometric ratio and equivalence ratios, and so on, how to calculate those. And also at end we'll also see how much energy is being produced then using the enthalpy of formation, how to calculate, and so on. So with that we'll dive straight into the problems. So first question is, we have a natural gas mixture having a molar analysis of 60% methane, 30% ethane and 10% nitrogen, which is supplied to a furnace where it burns completely with 20% excess air. So for this, determine what is the balanced reaction equation is, and next you need to find out the air fuel ratio both on molar and mass basis. So here the question is given in molar basis, so we did a molar analysis and we are burning natural gas in a furnace. So your inlet has 60% methane and 30% ethane and nitrogen 10% by moles. So if you take 1 mole, you have 0.6% methane, 0.3% ethane and 0.1% of nitrogen. That's what is there, and this is burned in a furnace which has 20% excess air. That means if you require for 1 mole, if you require 1 moles of air for complete combustion, then you have 20% excess. So using 20% more than what a stoichiometric ratio is required. So with that we need to find out what is the reaction equation will look like and what is the air fuel ratio both in molar and mass basis. So we consider per mole of fuel mixture because we know in moles how much quantities of the inlet is fuel is. So as I already said, so considering 1 mole, we have 0.6 moles of methane, 0.3% of ethane and 0.1% of nitrogen. So for a complete combustion with a theoretical amount of air, so if we write an equation like this, so your fuel plus air, so we don't know how much moles of air is required for complete combustion, so we'll take some alpha, and beta CO2 plus gamma H2O equals since we have excess air, so there will be some amount of nitrogen, this is stoichiometric, so we have same amount of alpha of nitrogen because nitrogen is not coming into combustion, so the same amount of nitrogen will be there as the products, and additionally the initial feed nitrogen which was there for the fuel natural gas mixture which contained 10% of nitrogen, that will also be there. So 3.76, so per 1 mole of nitrogen air you have 3.76 moles of nitrogen, and for 1 mole of oxygen in the air, so because you have 27% of oxygen and rest is of nitrogen, so work it out, we'll get 1 moles of oxygen contains 3.76 moles of nitrogen for air as a combined. So when we this is how the equation looks. Now we need to estimate how much moles each of the components are present. So what we'll do is we'll do individual atom balances. So we'll take first initially the carbon atom. So the left side will be equal to the number of carbon atoms present at the right side. So first is we have methane, we have 0.6 moles. So 0.6 times carbon with this one carbon atom in methane, 0.6 into 1, and then in ethane we have 2 carbon atoms, so 0.3 moles of ethane, so 0.3 into 2 equals the beta here, carbon is 1 in CO2, so beta into 1, so with this I get beta as 1.2 straight away. Next we will do an balance for hydrogen, so hydrogen similarly 4 into 0.6, so we can do a single hydrogen or a H2. Here we are doing H2, so 0.6 into 2 plus 0.3 into 2 3 equals 1 gamma, so gamma is 2.1. Next is O2 balance. So O2 here on the right side is alpha equals, you have beta times O2, so beta plus gamma, there is one O oxygen, there is no O2, so gamma by 2. So this gives us, we know beta and gamma, so substituting that we can find out alpha, so alpha comes out to be 2.25. So now alpha is 2.25, but since we are using 20% excess air, so multiplying this by 1.2, so gives us 2.7. So we will be using 2.7 moles of air. So now how the equation will look like. So 0.6 times CH4 plus 0.3 ethane plus 0.1 nitrogen, which is the natural gas, plus 2.7 times of air gives us 1.2 moles of CO2 plus 2.1 moles of H2O, plus since we have used excess air, so there will be some amount of oxygen, so 2.7 minus the stoichiometric value 2.25 times of oxygen plus the nitrogen will remain same, so 3.76 into the amount of air moles, so 2.7 plus 0.1 which was there in the natural gas. So this is how the complete equation will look like, and we'll get 2.7 moles, so 1.2 moles of CO2, 2.1 moles of water, and 0.45 moles of oxygen, and 10.252 moles of nitrogen. So this is how the balance reaction will look like with 20% excess air and complete combustion. Next is we need to find out air fuel ratio on a molar basis. So air fuel ratio is air by per moles of fuel, how much air we are using, how much moles of air we are using. So per oxygen we are using 3.76 moles of nitrogen, so combined air is 4.76 moles, so that has to be taken because air we are considering. So if you take 4.76 moles of air, we have get 1 moles of oxygen. So for every fuel we are taking 4.76 moles of air, and for complete combustion we require 2.7 moles of air. So 2.7 into 4.76 for 1 mole of fuel. So here we assumed that we are taking 1 mole of fuel, so that will remain same, or else we have to divide it by the number of moles of fuel. So 2.7 into 4.76 gives us 12.852. So that is the amount of kilomoles of air required per kilomole of fuel in molar basis. So similarly in mass basis, for mass basis what we will do is we convert this into mass, so for using molar mass or molecular weight. So we know number of mole is mass divided by molar mass, so a mole can be written as mass of the component into molar mass of the component. So we'll just multiply by molar mass of air divided by molar mass of fuel with the air fuel ratio in molar basis. So air fuel ratio in molar basis into molar mass of air divided by molar mass of fuel. So for fuel, now we need to find out the total molar mass. Since we know each of the composition of the fuel, we can estimate the molar mass of the fuel, and So 0.6 times methane, 0.3 times ethane, plus 0.1 times nitrogen. So 0.6 into what we do is n into your molar mass divided by total n. So here, since the number of moles is 1, so straight away 0.6 into 16.04 is the molar mass of methane, plus 0.3 into 30.07 is the molar mass of ethane, plus 28.101 is molar mass of nitrogen. So we can round it off to find out directly. See, carbon is 12 and hydrogen is 1. So CH4, 12 plus 4 times 1, so we'll get 16. So you can directly use 16, and similarly you will get 30, and nitrogen is 14. 14 into 2 will get 28. So we'll get 21.45 is the molar mass of the fuel, and molar mass of air is 28.97. So substituting the values here, we get 17.368. So it says that we need 17.368 kgs of air for burning 1 kg of fuel. So next question, we have a natural gas fuel mixture as the molar analysis shown below. So determine the molar analysis of the product for complete combustion with 70% excess dry air. So this problem is similar to what we saw previously. So similar to that, so here we have ethane 25%. This is also in molar basis. So methane, hydrogen, and ammonia. That's what we have. So methane 25% and hydrogen 30% and ammonia is 45%, and we are using 70% excess dry air. So just like the previous one. So we are writing methane 0.25, 0.3 times hydrogen, and 0.45 times ammonia. And for a complete combustion, similar approach, A oxygen plus 3.76 nitrogen gives P moles of carbon dioxide and C moles of water and D moles of the nitrogen. So doing a carbon balance, we will get straight away B is 0.25, and then doing a hydrogen balance, so 4 times of 0.25, we can again we can take a single atom hydrogen or a double hydrogen pair H2. So here H, so 4 times 0.25 plus 0.3 times into 2 plus 0.4 times 45 times into 3 gives us 2C for a water molecule. So with this, dividing the whole thing by 2 and calculating C, we get 1.475. So we get 1.475 moles of water. And doing an oxygen balance next. So here if you see 4 unknowns are there, A, B, C and D. So we need to find out 4 equations. So that's what we are doing, getting each of the equations from each of the atom balances. So we got carbon and hydrogen. Next is oxygen, and similarly oxygen is A times 2 into 2 because O2 molecule in air. So 2A equals CO2, so 2 into B plus oxygen, there is one molecule in water, so C times 1. So with this we know A and we know C and B, so we can find out A. So A comes out to be 0.9875. Then ammonia, so ammonia nitrogen balance, so 0.45 times 1 plus 3.76 into 2 in nitrogen air times A plus 2D. So we have found out A, so substituting the value we get D as 3.938. So this is how the equation with the theoretical air or stoichiometric air for complete combustion looks like. 0.25 times of methane plus 0.3 times of hydrogen plus 0.45 times of ammonia gives 0.9875 moles of air combusting to give 0.25 moles of carbon dioxide plus 1.475 moles of water plus 3.938 moles of nitrogen. So when we are combusting with 70% excess air, so similarly we have to use 1.7 times of what moles we got for theoretical air, so 1.7 times into 0.9875, and doing again each of the atom balances, we get A as 0.25, which will remain same, and hydrogen will get 1.475 B. This is also same because this is all complete combustion, so the amount of moles of carbon dioxide and hydrogen will remain same. The only thing which will change is we will have excess oxygen and nitrogen. So C we are getting at 0.69125 and D 6.5371. So that is only change. So if you see nitrogen here, we were getting 3.938. So because we are getting 70% air, the only thing change will be in the moles of oxygen and nitrogen, and this is how the expression will look for 70% excess air. Now we need to calculate the mole fraction for each of the product. So that is nothing but you mole divided by the total number of moles. So on the product side, if you see, we have 0.25 moles of carbon dioxide and 1.475 moles of water, then 0.69125 of oxygen, and rest is nitrogen 6. So we are adding up, we'll get the total moles of the product which is present. So that will come out to be 8.95335. So that is the total number of moles. So dividing it by each of the component moles, we'll get the mole fraction. So for carbon dioxide, 0.25 moles of carbon dioxide, so 0.25 divided by total number 8.95338 gives you 2.8%, and similarly water is 16.5%, and oxygen is 7.7%, and nitrogen is 73%. So moving on to next question. We have a gaseous fuel mixture with a molar analysis of 70% methane, 10% hydrogen, 12% nitrogen, 3% oxygen, and 5% carbon dioxide, which burns completely with moist air to form gaseous product at 1 atmosphere consisting of carbon dioxide, water, and nitrogen only. So the humidity ratio of the moist air is 0.01 kg of water per kg of dry air. Determine the dew point temperature of the products. So we have the mole fractions of the fuel which is coming, we are burning it, and we know we are not using dry air, so we are using moist air, and they have said gaseous product contains only CO2, H2O, and nitrogen. So that means we have complete combustion, and there is no excess oxygen, so theoretical air. So and next is the humidity ratio of the moist air is given. It contains 0.01 kg of water per kg of dry air. So we need to find out the dew point temperature. So we'll see how to solve this. So this is how it looks. So the fuel which is coming in, we'll assume it to be 1 mole because it's given in molar analysis. Okay, moles. And moist air, omega is 0.01 kg, and the gaseous product contains CO2, H2O, O2, and nitrogen. So here maybe I think I missed O2. Okay. So the dew point temperature is the saturation temperature that corresponds to partial pressure of the water vapor in the product. So we need to for that we need to find out the partial pressure of water vapor. So corresponding saturation temperature will be my dew point temperature. So to start with, we need to find out how much initial to do the calculation. We need to know how much moles of water is present. So the moles is mass of water divided by your molar mass will give you the moles. Mass of water is not known, but what we know is specific humidity, or the omega times mass of air. So mass of water is omega into mass of air, and mass of air we can write in terms of moles. So moles into mass of molar mass of air into number of moles of air. So we get omega into moles of air into molar mass of air divided by molar mass of water. So substituting the values here, so molar for 1 mole of oxygen we are having 4.76 moles of air. So with that we substituting n of air as 4.76, and molar mass of air is 28.97, and what water is 18, and omega is given as 0.01. So we'll get the moles of hydrogen water is 0.0765 kilomole of water. So next is for 1 kilomole of fuel if we are combusting. So we have 0.7 moles of methane, 0.1 mole of hydrogen, 0.12 moles of nitrogen, and 0.03 moles of oxygen, and 0.05 moles of CO2, which is combusted with now we are considering moist air. So plus A, O2 plus 3.76 moles of nitrogen, which is the dry air, plus each 4.76 moles of dry air will contain 0.0765 moles of water. So that times A equals, we have only CO2, H2O and nitrogen. So B CO2 plus C H2O plus DN2. So that is a product. We need to find out now the coefficients to find out the number of moles present in the product, and number of moles of air required. So again going with each of the component atom balances. So carbon we have 0.7 times in methane, and then we have some amount of CO2 present, so plus 0.05 gives B is 0.75. Then doing a hydrogen balance, 0.7 into 4 plus 0.1 into 2 gives plus 0.0765 into 2 into A gives 2 times C. So we get one expression, C equals 1.50 plus 0.0765A. So that is one equation. Next we'll do an oxygen balance. So 2 into 0.03 plus 2 into 0.05 for our carbon dioxide, plus 2 into A for the oxygen in air, and 0.0765A for water. And similarly the other side we have 2 times of B plus C. So we know B, substituting B 0.75, we get one more equation in terms of C and A. So here A is 0.64532 plus 0.48158 C. And now we have two equations with two unknowns. So solving it, we get A is 1.42, and substituting that value in one of the expression, we get C as 1.60863. So next only unknown is left is D. So doing a nitrogen balance. So we'll start 0.12 into 2 plus 3.76 into 2 into A gives D into 2. So D comes out to be 5.4592. So ultimately this is how the balanced chemical reaction will look like for a complete combustion for with the moist air. So we have fuel, and A is 1.42, which we found out. So we require 1.42 moles of air, 42 into 4.76 moles of air, dry air, which gives you 0.75 moles of carbon dioxide and 1.60863 moles of water and 5.4592 moles of nitrogen. So CO2, H2 and N2 is the product, so we need to find out the mole fractions on the product side to find out the partial pressure, because partial pressure can be found out using the total pressure and the mole fraction using Dalton's partial pressure law. So CO2 we have 0.75 moles, and water similarly 1.6086 and nitrogen 5.45. We are adding up, we will get the total number of moles in the products as 7.81783. So that is the amount of moles present in the product. So for water, the mole fraction is 1.60863 divided by the total moles 7.81783 gives you 0.206. So 20% of water is in the product side. So so here the question, assuming it is happening all at atmospheric pressure, so your 1 atmospheric pressure is 1.01325 bar times your mole fraction gives you partial pressure of water vapor. So 0.206 into 1.01325 gives you 0.209 bar. So from the steam table corresponding to 0.209 bar, your saturation temperature is 60.9 degree Celsius. So the dew point is 60.9 degree Celsius. So similarly, the next question is, we have methyl alcohol. So the molecular formula is CH3OH, which burns with 200% theoretical air, yielding CO2, H2O, O2 and nitrogen. So determine the balanced reaction equation, B air fuel ratio on mass basis, and C molar analysis of the products. So this procedure will remain same. We have now, instead of other components, we have one fuel of methyl alcohol, and it's burning with 20% theoretical air, 200% theoretical air, twice of theoretical air. So first we need to find out the equation for complete combustion with the theoretical air, and what will be the expression for we are having using twice of theoretical air, and then we can find out the air fuel ratio and find out the mole fractions of each of the product components. So first again we need to find the balanced equation. So CH3OH plus A times of air, which is oxygen plus 3.76 nitrogen, gives you BCO2 plus CH2O plus D nitrogen. So just like the previous questions, we need to do each of the component balances. So we have 4 unknowns, we need to do get 4 equations. So we'll do 4 of the molecule balances, atom balances. So carbon atom first. So we have 1 carbon atom in the fuel. Yeah, so 1 equals B times of 1 for 1 atom in CO2. So we get B straight away 1. Next is hydrogen balance. So in fuel we have 4 hydrogen atoms. So 4 equals, there is a hydrogen atom in water. So 2 times of C. So C comes out to be 2. Then we'll do an oxygen balance. So fuel has 1 oxygen atom plus 2 times of A in air gives you 2 times of C, 2 times of B in for CO2 and oxygen 1, so plus C. So we get 1 plus 2A equals 2B plus C. So we know C and B. Substituting the values, we get A as 1.5, and then we'll do a nitrogen balance. So 3.76 into 2 into A for air. We have 2 nitrogen atoms, 2. So 2 into 3.76 into A equals 2 into D. So we get A as D is 5.64 because A is 1.5. So 3.76 into 1.5 is 5.64. So the balanced reaction for theoretical air is we have 1 mole of methyl alcohol plus it requires 1.5 moles of 4 into 4.76 moles of air. And 1.5 moles of air and gives you 1 mole of CO2, 2 moles of water and 5.64 moles of nitrogen. So instead of 1.5 moles, if you use twice the theoretical air, so we will be using 3 moles of air. So that will give you the same amount of carbon dioxide and hydrogen, but we will have excess oxygen and nitrogen. So again doing the same balances. So additionally we have 1.5 moles of oxygen and 3.76 into 2 into 1.5 moles of nitrogen, that is 11.28. So this is how the expression will look like. So we have 1 moles of methyl alcohol combusting with 3 moles of air, giving you 1 mole of CO2, 2 moles of water and 1.5 moles of oxygen and 11.28 moles of nitrogen. Next is we need to find out the air fuel ratio in mass basis. So air fuel ratio, we'll first find it in molar basis. So we are having 3 into 1 mole of air contains 4.76 moles of oxygen plus oxygen and nitrogen. So 3 into 4.76 divide by 1 kilomole of methyl alcohol. So 3 into 4.76 is your molar air fuel ratio into your molar mass of air divided by molar mass of fuel. So molar mass of fuel again you can find out using 12 plus 4 into 1 plus oxygen is 16. So 16 plus 12 is 28 plus 4 32. So you get 32 for molar mass of fuel. So we get 3 into 4.76, which is the number of moles of air, into 28.97, which is the molar mass of air, divided by 32.04 molar mass of the fuel, gives you 12.91 kg of air, which is required per kg of methyl alcohol. So that is the air fuel ratio. So theoretical will be half of this because we are using 200%. The theoretical air fuel ratio will be somewhere around 6.4505. Next is we need to find out the molar analysis of the products. So we need to just find out the mole fractions. So again the products are CO2, H2O, O2 and nitrogen, and the corresponding moles present are CO2 1 mole, H2O is 2 moles, oxygen is 1.5, nitrogen is 11.28. So if we add up all the moles, we will get 15.78 moles of product. So mole fraction, we divide each of the mole of the component divide by total moles. So for CO2, 1 by 15.78 gives you 6.34%, and similarly water, H2O is 2 divided by 15.78, which gives you 12.67%, and oxygen is 1.5 divided by 15.78, which is 9.51%, and then nitrogen is 11.28 divided by 15.78, which is 71.48%. So that ends the molar analysis of the product. So next question is again a similar question. So octane is burned with 20% excess air, yielding carbon dioxide, CO, oxygen, O2, and H2O, and nitrogen. So we are burning with excess air 20%, but we still have CO, so there will be no complete combustion. So what is given is we are burning octane with 20% excess air, and the product contains only CO2, CO, O2, H2O, and nitrogen. So if out of this, if 5% of the dry product molar basis is oxygen, we need to find out the balance reaction equation and the analysis of the products on a dry molar basis. So dry molar basis, we need to not consider water. So for first, assuming a complete combustion in octane, so the theoretical amount of air which will be required is so to know that how much amount of air which been used, we need to find out, because the question says we are using 20% excess air. So for that we need to find out the theoretical air first. So we'll assume first a complete combustion is happening. So for octane, C8H18, so that is molecular formula is given, C8H18. So 1 mole of C8H18 reacts with similarly A plus O2 plus 3.76 N2 gives B CO2 plus CH2O plus D N2. So solving that, we'll get C8 A is 12.5 and 8 moles of carbon dioxide, 9 moles of water, and 47 moles of nitrogen. So now it has to combust with 20% excess air. So we will multiply 12.5 with 1.2. So this is how the expression will look like. So C is 8 on the right side plus 8 moles of CO2 plus B moles of CO, because there is some CO present. So that will give you B is 8 minus A. Then hydrogen balance, we have 18 moles of hydrogen, which is equals to 2C. So expression will be like this: C8H18, which is the octane, plus 12.5 into 1.2 times O2 plus 3.76 nitrogen gives you A moles of CO2, B moles of CO, plus C moles of H2O, plus D moles of nitrogen. So with that, doing this balance, so C is 8 equals A plus B for A moles of CO2 and B moles of CO, and 18 on the right side for hydrogen, and C moles of water, so 2C. So C comes out to be 9. Then oxygen, so 12.5 into 1.2 into 2. So 12.5 into 1.2 is 15. So 15 into 2 is 30. So 30 on the right side, and we have 2 moles in CO2, so 2A, and 1 mole in oxygen, CO. So B plus B, and then oxygen 9 moles of water. C we have found out to be 9, so C plus oxygen, there is some amount of oxygen, so 2D. So this comes out to be A equals 13 minus 2D. So the total moles of dry product is A plus B plus D plus 56.4, which is the nitrogen which will be present, which is 12.5 times 12.5 into 1.2 into 3.76. That is the amount of nitrogen which will be present. So that is 56.4. And we don't know oxygen because some is combusting to CO2 and some is there in CO. So we will have somewhat more oxygen present. So we need to find out oxygen. So nitrogen we can straight away find out because it's not taking part in combustion. So excluding water, the number of moles present is the number of moles of dry product. So A plus B plus D plus 56.4 is the products of dry product mole number of moles. So here substituting the expressions here. So and keeping it in terms of D. So they are saying we are keeping it in terms of D because oxygen is the D amount of oxygen present. So in the question it is mentioned that 5% of the dry product is oxygen. So mole fraction is 0.05, which is number of moles of oxygen divided by the total number of moles of dry product. So number of moles of oxygen is D divided by D plus 64.4, which is the total number of moles, gives you D is 3.389. So once D is known, we can find out A using the oxygen balance, substituting here, and then substituting A for finding out B. So substituting that, we will get the final expression for the combustion equation. So 1 moles of octane reacts with 15 moles of air to give 6.222 moles of CO2, 1.778 moles of CO, and 9 moles of water, and 3.389 moles of oxygen, and 56.4 moles of nitrogen. So next is needed to find out the molar basis, dry molar basis for the products. So we need not consider water in this. So the dry product total number of moles is D plus 64.4. So D, substituting the values of D 3.389, we get the number of moles of dry product as 67.789 moles. So mole fraction of each of the component will be, so CO2 is, we got 6.222 moles of CO2. So moles of CO2 divided by the total moles gives you 9.2%, and similarly CO we had 1.778 moles divided by the total number of moles gives you 0.026, with 2.6%, and CO2 is 3.389, sorry, oxygen, and this is not CO2, this is oxygen, which is straight away given in the problem as 5%. So we will get the same. And next is of nitrogen. So nitrogen will be 56.4 divided by 67.789 gives you 83.2%. So that's how we calculate when the molar mass or molar ratio for oxygen is given at the product. So that's how we estimate the remaining quantities. And next is we have a flexible fuel vehicle which operates with a stoichiometric fuel mixture of 1/3 isooctane, 1/3 ethanol, and 1/3 methanol by mass. So previously we saw it all in moles. Here they have given in terms of mass. So we have 1/3 by moles mass by mass fraction of isooctane, 1/3 by mass of ethanol, and 1/3 by mass of methanol, which is mixed together and then used as fuel for a vehicle, and it's burning it stoichiometric fuel mixture. So for this we need to find out the air fuel ratio. Excuse me. So this case we need to find out the air fuel ratio. So first is what we know is considering that we have 3 kgs. So because we are considering in mass, so each 1 kg. So we have 1/3 proportion for each of the component. So first is octane. So isooctane or it will be the molecular formula will be same as octane. So C8H18. Then we have methanol CH3OH, and then ethanol C2H5OH. Each 1 kgs. So the molar mass of each of the components is, so octane is 114. So C8 to 8 into 12 plus 18, so we get 114, and we have methanol which is 32 and ethanol which is 46. So using this we'll find out the number of moles. So number of moles is mass by molar mass. So the N is now 0.00877, which is 1 by 114, and similarly 1 by 32 0.03125, and 1 by 46, which gives you 0.02174. So adding up we'll get the total number of moles is 0.06176. So next is we'll find out the mole fraction. So to find out if we consider 1 mole of fuel, how much moles each moles will contain. So first is octane. We have 0.00877 divided by 0.06176 will give you 0.142, and similarly methanol is 0.506 and ethanol is 0.352. You see adding up to 1. So if we have take a combination of this as 1 mole, that 1 mole will contain 14.2% of octane, 50.6% of methanol, and 35.2% of ethanol. So if we write a balance equation, so similarly, so we take 0.142 C8H18 plus 0.506 into CH3OH plus 0.352 C2H5OH plus A times O2 plus 3.76 nitrogen gives you BCO2 plus CH2O plus D nitrogen for complete combustion. And do each of the component balances, atom balances for carbon, hydrogen, oxygen and nitrogen. So this is how the values will be, and this is the balanced equation which you will get at the end. So which will give you 0.142 moles of octane, 0.506 moles of methanol plus 0.352 moles of ethanol reacting with 3.59 moles of oxygen, and you have 3.5 into 3.76 moles of nitrogen which will be present in the air, and then gives you 2.346 moles of carbon dioxide and 3.346 moles of hydrogen or water, and 3.59 into 3.76 moles of nitrogen which will be present. So air fuel ratio is your mass of air divided by mass of fuel, which we can find it out using air fuel ratio in molar basis multiplied by molar mass of air divided by molar mass of fuel. So we know we are using 3.5 moles of air, so 3.59 into 4.76 into your you can use 28.98 or 29 divided by your moles of air, which is moles of fuel is 1, and you need to find the molar mass. So molar mass is 0.142 into molar mass of each of the component into each of the mole fraction. So 0.142 into octane molar mass is 114, so 0.142 into 114 plus 0.506 into 32 plus 0.352 into 46. So this will give you air fuel ratio as 10.2. So next is fuel. There's some conversion error happening here. So fuel contains, I'll straight away show it in problems. So we have CXHY, which is the molar formula for the fuel. So that is combusting with air, dry air, and the product contains the dry molar basis 9.6% of CO2, 7.3% of oxygen, and 83.1% of nitrogen. I think I'll just edit it here. So CXHY reacting to form 9.6% of CO2, 7.3% of O2, and 83.1% of nitrogen. We need to find the fuel composition X and Y and the percent theoretical air used. So we'll assume that some moles of fuel is used, because we cannot assume 1 mole because we don't know how much it is combusting to form this product ratio which is given. So some moles of fuel and fuel composition is not known. So CXHY plus moles of oxygen O2 plus 3.76 into moles of oxygen into nitrogen gives you 9.6 CO2 plus 7.3 O2 plus 83.1 nitrogen. You can straight away write it as 0.096 also. so plus moles of hydrogen water. So this is how the expression looks, because in the question it is given as a dry mole basis, so they are not considering water, but some water will be present. So doing an individual component atom balances, so N2 balance, so 3.76 into your mole of oxygen gives you 83.1. So the moles of oxygen which is present is 22.101. Similarly, oxygen balance, so we know now, so mole of oxygen equals 9.6 plus 7.3, which is present oxygen, plus half into your moles of water. So we know moles of oxygen, substituting that we can find out moles of water, which is comes out to be 10.402. Next is hydrogen balance, so moles of fuel into Y gives you 2 moles of oxygen. So oxygen is known, moles, so substituting that we can find out moles of fuel into Y as 20.804. Next is carbon balance, so X into mole of fuel gives you 9.6. So we are asked fuel composition ratio, so X by Y, so X by Y is nothing but 9.6 divided by 20.804, because the number of fuel moles will get cancelled out, so we'll get 0.461. So that is the fuel composition ratio. Then we need to find out the theoretical air. So theoretical air is your oxygen, number of moles of oxygen divided by the stoichiometric air value required. So this gives you the actual moles of oxygen used, 22.101, divided by the oxygen which would have been required, that is 9.6 into 2, oxygen is O2, so 9.6 plus 7.3 plus half into 10.402. Think so small mistake here, we 20.804 into 0.5 plus 9.6. So when we are doing complete combustion, we'll have CO2 plus water. So 22.101 is the current mole of oxygen, divided by 9.6 plus half into moles of water, which is 20.804. So half into 20.804, which will come out to be 1.1013 or 110.3%. 0.01. So here answer is correct. Here the only change is half into 10.402. So we'll get 149.3. I calculated with respect to 20.8042, so I was getting 110. Here your number of moles of oxygen which is present is 10.402. So 22.101 divided by 9.6 plus 1 by 2 into 10.402. So that will be theoretical stoichiometric moles of air which is required is comes out to be 14 moles. 14.8 moles. So here we are using 22.101 moles of oxygen, and for complete combustion your stoichiometric value is 14.8. So 22.1 divided by 14.8 gives you 149.3%. So next is in an engine, liquid octane and ethanol with a mole ratio of 9:1, and stoichiometric air are taken in at 298 Kelvin and 100 kilopascal. After complete combustion, the products run out of the exhaust system where they are cooled to 10 degrees Celsius. Find the dew point of the products and the mass of water condensed per kilogram of fuel mixture. So we are given the ratio in which octane and ethanol are formed to form the fuel, and they are combusting with the stoichiometric air, and we need to find out the dew point and the mass of water which is present when it's cooled to 10 degrees Celsius. So first we'll write the equation, combustion equation. So similarly doing a component balances and finding out each of the moles of the components. So we have 0.9 moles of octane and 0.1 moles of ethanol, so E2H5OH. So 0.9 and 0.1. And which is combust with again E plus O2 plus 3.76 nitrogen gives you BCO2 plus CH2O plus T nitrogen. You find out each of the values using each of the atom balances, and this is what you get. So 0.9 moles of octane plus 0.1 moles of ethanol plus 11.55 moles of oxygen plus 43.428 moles of nitrogen gives you 8.4 moles of water, 7.4 moles of carbon dioxide, and 43.428 moles of nitrogen. So with this, now we need to find out dew point temperature. So to find out dew point temperature, we need to find out the molar fraction of water, to find out the partial pressure of water vapor. So the mole fraction of water is, we have 8.4 moles of water divided by the total moles present in the product. So 8.4 plus 7.4 plus 43.428 gives you 0.1418. So 0.1418 into, again, the total pressure gives you 14.3 kilopascal. So the corresponding dew point temperature is 52.9 degrees Celsius. Since we are combusting with this cooled to 10 degrees Celsius, the vapor pressure corresponding to 10 degrees Celsius is 1.2276. So we are finding out mole fraction from using the vapor pressure. So at 10 degrees Celsius, your pressure is 1.2276, and divide by total pressure will give you the mole fraction. So that is comes out to be, since it is at pressure of 100 kilopascal, so divide by 100 gives you 0.012276. So that is the mole fraction of the water, which is equals to x moles divided by x moles of water plus 7.4 moles of carbon dioxide plus 43.428 moles of nitrogen. So the only unknown is x. We can find out x, which comes out to be 0.6317. So initially we had 8.4 moles of water, out of which the rest condensed, and we have left out with 0.6317 moles of water. So the change in moles is 7.77 moles, which has condensed. So we need to first find out the mixture molar fraction of fuel. So 0.9 into 114.23 plus 0.1 into 46.069 gives you 107.414. That is the molar mass, and for water is 18. So for 1 mole of fuel, multiplied by 107.414 gives you mass of fuel which is used. So since we need to find out the water condensed per kilogram of fuel, so we have to divide by mass of fuel which is used for combustion. We have calculated assuming 1 mole of fuel, so we are converting that to mass. So 1 into molar mass of fuel will give you mass of fuel, and again the mass of water which has condensed is the change in moles of water, which is 7.77 into your molar mass of water, which is 18. So 7.77 into 18.015 divided by 107.414 gives you 1.303 kgs. So 1.303 kg of water is condensed per kg of fuel. So next question is, find the stoichiometric air fuel ratio for the combustion of ethyl alcohol in a petrol engine. Calculate the air fuel ratio for the extreme mixture strength of 80% and 130%. Determine also the wet and dry analysis by volume of the exhaust gas for each mixture strength. So equation of combustion for ethyl alcohol is C2H6 oxygen C2H6O plus 3 oxygen, and each will have 3 into 4.76 moles of nitrogen, because nitrogen will not come into participate in the reaction. So we can find out O2 plus CO2 plus H2O, and finding out each of the moles by component atom balances, we get C2H6O plus 3O2 gives you 2 CO2 plus 3 H2O, and there will be some nitrogen, so 3 into 4.76, which is 79 by 21. the proportion in which nitrogen and oxygen are there. And 2 CO2 plus 3 H2O plus 3 into, again that's the expression. The oxygen required per kg of fuel is, so 1 mole of fuel has in terms of mass is 46 kg, and it requires 3 moles of oxygen, so which is 96 kg. So oxygen required per kg of fuel is 96 by 46, which is 2.09 kg. So stoichiometric air fuel ratio is 2.09 divided by by 0.233, which gives you 8.96. So similarly, if we consider 80% mixture strength, so stoichiometric is 8.96 divided by actual air fuel ratio is 8.8, so actual air fuel ratio is 11.2%. So calculating, so we require 11.2, so 1.8 says that 1.25 times of air, so we are using 25% excess air, so C2H6 plus 1.25 times of the moles of air. So this is how the expression, balance expression will do. So this gives you the same amount of moles of CO2 and H2 will be present. So we have excess of oxygen now, 0.25 into oxygen plus and nitrogen. So this is how will look like, and that product contains 2 plus 3 plus 0.75 plus 14.1 nitrogen, so 19.85 moles of product. So in wet analysis we consider water as well. So for molar balances, so CO2, number of moles of CO2 by total mole, so 2 by 19.85 gives 10.08%, and water similarly 15.11%, and oxygen is 3.78%, and nitrogen is 71.03%. In dry analysis, we exclude water and find out. So in that case, CO2 is 11.87%, oxygen is 4.45, and nitrogen is 83.68%. So there we need exclude water, and that we also exclude from the total moles. So we calculate only the other components. And similarly, when we have 1.3% of equivalence ratio, so 1.3 is stoichiometric air ratio by actual air fuel ratio. So strength, so 1.3 stoichiometric by 1.3, so it gives 6.89, or we have 1 by 1.3, so which is 0.769. So we are using less air, we are using less than stoichiometric air, so there will be incomplete combustion. So in that case, we write this equation, C2H6O plus 0.769 gives you ACO2 plus BCO plus 3H2O and the nitrogen. So you're doing again carbon, oxygen and nitrogen balances. we find out the A, B and values. So it comes out to be 0.614 moles of CO2, 1.386 moles of CO, 3 moles of water and 8.678 moles of nitrogen. So the total moles will be 13.678, and we do similarly wet analysis and dry analysis. And CO2 we get 4.49%, CO is 10.13%, water 21.93%, nitrogen 63.45%. And dry analysis we remove water and we calculate for the rest of it. So we get total moles of 10.678, and similarly the mole fractions 5.75 for CO2, 12.98 for CO, and 81.27 for nitrogen. So a sample of fuel has the following percent composition by weight. So carbon 84%, hydrogen 10%, oxygen 3.5%, nitrogen 1.5%, and the ash is 1%. So we need to find stoichiometric air fuel ratio by mass. 20% excess air is supplied. Find percentage composition of dry flue gas by volume. So by volume is mole percent again. Can use mole in terms of volume. So on the basis of 100 kg of fuel, let us assume an equivalent formula. So CaHbOCND. So this is how the molecule or the formula for the fuel is, because we know this percent of the composition for the fuel. So for the given analysis by weight, we can write, so because the composition is given by weight, we are converting into moles. So 12A equals 84, so A is 7, 1B equals 10, so B is 10, 16C oxygen is 3.5, so C is 0.218, and 14D is 1.5, so D is 0.107. So this is how the formula looks: C7H10, O 0.218 and N 0.107. So for this, if we write a combustion equation, so this is how the expression looks. So we do again each of the atom balances to find out the expression. So 7 equals P. So again hydrogen balance, and then oxygen balance and nitrogen balance. So we get the moles of each of the components. So this is how the final balanced expression will look like for combustion. So we will require 9.39 moles of air to give 7 moles of CO2, 5 moles of water, and 35.4 moles of nitrogen. So stoichiometric air fuel ratio is, so 9.39 into 32 plus 9.39 into 79 by 21 into 28. We are finding out the mass, divided by, we are assuming 100 kg of fuel, so divided by 100 kg of fuel, which gives you 12.89. So that is the stoichiometric air fuel ratio. So percentage composition of dry flue gas by volume with 20% of excess air is, so same 9.39 into 1.2. So we'll have some extra oxygen and nitrogen, which is 0.2 into 9.39 oxygen, and 1.2 into 9.39 into 3.76 of nitrogen. So the number of moles of products is, dry products is 7 moles of CO2 plus 0.2 into 9.39 of oxygen and 1.2 into 35.4 of nitrogen, which comes out to be 51.358. So dry gas by volume is equivalent to mole fraction. Volume fractions and mole fraction will be same. So if you assume C ideal gas equation, PV is nRT, N is the number of moles, so V and moles are proportional. So CO2, you write moles of CO2 divided by total number of moles, which gives you 13.63%, and oxygen is 1.878 moles divided by total number of moles, which gives you 33.66%, and nitrogen gives you 82.71%. So next question is, we have acetylene gas C2H2 is burned with stoichiometric air in a torch. The reactants are supplied at the reference condition of PO and TO. The product come out from the flame at 2500 Kelvin after some heat loss by radiation. So find the heat loss per kilomole of fuel. So for reaction equation for acetylene is C2H2 plus 2.5 times of air moles of air gives you 2 moles of CO2 plus 1 mole of water plus 9.4 moles of nitrogen. So if we write an energy equation, which is your enthalpy of product plus the heat gives you enthalpy of the reactant. So the enthalpy of product is formation plus the enthalpy change of the product plus heat let out equals the enthalpy formation for the reactant. So the enthalpy change of the product is from T0 to 2500. So substituting the values from the table, so this is what you get for CO2 1219 to 6.5, and similarly for water and nitrogen. So you get 1041418 kilojoule per kilomole, and so Q out will be the difference between the reactants and product values. So the enthalpy formation of fuel for acetylene, so we see here acetylene is 226731. So substituting 226731 minus for water and CO2. So similarly for water from the table, water which is 28530 and CO2 393522. Substituting the value and the enthalpy of change, so it gives you the heat let out is 214183 kilojoule per kilomole of fuel. So next is, we have butane gas and 200% theoretical air, both at 25 degrees Celsius. So enters a steady flow combustor. So the product of combustion exits at 1000 Kelvin. So calculate the heat transfer from the combustor per kilomole of butane burned. So butane reaction, so with 200% theoretical air, so C4H10 plus 1 by 5 is the equivalence ratio into number of moles of air used, O2 plus 3.76 nitrogen equals ACO2 plus BH2O plus CN2 plus DO2. First we do it for stoichiometric air when phi is 1, so D is 0, and doing each of the atom balances, we get A as 4, B as 5, and the number of moles of oxygen is 6.5. So and C will be again 6.5 into 3.76. Similarly, when we are having equivalence ratio of 2, so phi is 0.5, so it will be 2, so 2 times of 200%, so 2 times of oxygen moles which are used, 6.5, so 2 into 6.5, which gives you 13. And similarly A and B will be same, so nitrogen will be 3.76 into 13, which is 48.88, and D will be 13 minus 6.5, the previous case, so it will be 6.5. And the energy equation will be again reactant minus product, and product will be formation minus the enthalpy change. So H naught R minus reactant will be for methane. So for methane is 74873, sorry, C4H10, it's butane. N-butane is 126200, 126200 kilojoule per kilomole. And similarly for product is we have 4 moles of CO2 and 5 moles of water. So 4 into CO2 carbon dioxide 393522 and water is 241826. So we give minus 2783 218 kilojoule per kilomole of fuel. So the rest of the values are at 1000 Kelvin. So the enthalpy change to 1000 Kelvin. So we get 33397, and for nitrogen 21463, and oxygen 22703, and water is 26000 kilojoule per kilomole. So with respect to multiplying with respect to corresponding moles, we get the enthalpy change of the product to be 1460269 kilojoule per kilomole. So substituting the values here, we get Q as 11,96749 kilojoule per kilomole of butane. So that is the heat which is released, the heat transfer when the butane is burnt. With that, I finished the questions which I had prepared for today. Next week we'll continue with this combustion problems. I'll also see at finding out adiabatic flame temperature and some more with energy balances on combustion. So thank you. So we'll see next week on continue on this combustion.